Good morning everyone and welcome to Nehru Science Center. Today we are starting the first lecture of our lecture series. This is Juma Ghosh, curator at Nehru Science Center, Mumbai. Every year on the occasion of International Women's Day, we organize various programs, contests and lectures. This year we have moved to the online platform mainly. I feel proud to say that not only the women in science but the women from all categories have significantly contributed in combating the COVID-19, and we have tried in our own way to do the best. To pay respect to those women, the theme of the International Women's Day 2021 has been set as Women in Leadership, Achieving an Equal Future in a COVID-19 World. For this reason, we have organized a lecture series as a follow-up of Vigyan Samaga, many of me may have attended also, where we will help the students to explore various career opportunities in future if they choose to work in the frontiers of science. Today's speaker is Professor Debarati Chatterjee. She will be talking about the future opportunities for Indian girl students in LIGO India project. Professor Debarati Chatterjee is an associate professor at IUCAA Pune. Her research interest mainly involves the developing the theoretical models of compact stars to confront the astrophysical and gravitational wave data. She is a member of the LIGO India Mega Science Project and coordinating their education and public outreach activities. With these words, I'd like to thank Professor Chatterjee for accepting our invitation, and I'm handing it over to her.
I thank sincerely the Nehru Science Center Mumbai for this invitation, and also congratulate them on this wonderful effort for organizing this series of lectures on mega science projects on the occasion of International Women's Day. It's my great pleasure to participate in this and to be able to represent LIGO India team. So I will share my screen. All right, so as Chuma already mentioned, my name is Debarati Chatterjee. I'm an associate professor at the Inter-University Center for Astronomy and Astrophysics in Pune, and a key member of the LIGO India project. So let me give you a brief outline of what this project is all about. So you know that with the advance of technologies, we have at our disposal today a large number of ground-based and space-based facilities, right? So telescopes. So with the help of these telescopes now, we can scan the entire sky from gamma rays through X-rays, from gamma rays through X-rays, infrared, microwave, and radio. So just like medical imaging, we can now scan the entire sky throughout the electromagnetic spectrum. So our eyes are only, can you see my cursor? You can, right? Okay, so our eyes are only perceptible to the visible part of the spectrum. So when we look up to the sky, we see stars only in this range. But then with the help of these telescopes, we can now scan the entire sky throughout this electromagnetic spectrum, throughout the different frequencies. So this gives us a lot of information about objects that are invisible to our eye, but can be seen now in great detail, okay? So you see this image at the bottom, which is at multiple frequencies. This is an object called the Crab Nebula. And inside the Crab Nebula, you can see that at different frequencies, you can see the interstellar dust. But with the help of X-rays, one can look into the nebula and see the compact star inside. So to know more about the compact star, let me tell you that this was first discovered by a young PhD student called Jocelyn Bell, who was working at the Cambridge University. So she first observed some wriggles in radio frequencies with her telescope. And from that, she pointed out that this must be some kind of extraterrestrial source. And now we know that this is actually an object called a pulsar, which you were able to see in X-rays inside this Crab Nebula. And these pulsars are nothing but very compact stars, which are rotating very rapidly, and they are emitting an electromagnetic beam along the magnetic axis, which sweeps towards us like a lighthouse, and we observe these very regular pulses. So, not only pulsars, there are also many other massive compact stars in the universe. So how are these formed? These compact stars are actually formed at the end point of the evolution of stars that we see. So the sun, is a star, right? So a sun is a light star, and these kind of light stars, they glow because they burn fuel inside their interior, and this fuel produces thermal pressure support against gravitational collapse. So because of this, these stars keep burning like big balls of fire. But when they run out of this fuel, they start to collapse towards the center and are stopped by a kind of a quantum mechanical pressure, which produces these kind of objects which are invisible to our eye, but they are extremely dense. So some of the most extremely dense and compact objects in the universe are shown here in this figure. So you see, they are called white dwarfs, neutron stars or pulsars, black holes. So these objects are among the densest in the universe. But as I told you, that some of these may not emit light that is observable with the telescopes that we have today. So how can we observe these objects? So let's now look at the story of gravity. So Einstein, back in 1915, proposed the general theory of relativity as the theory of gravity. So earlier, Newton had proposed that gravity is nothing but forces, like he said, okay, there's a falling apple because the apple is attracted towards the center of the earth. So gravity is nothing but an attractive force between massive bodies. But now this picture changed with the general theory of relativity that was introduced by Einstein. And now he proposed that that gravity is a force which results, it is a property of space-time. Space-time is nothing but the coordinates with which we can describe a massive object. So you can see that in this cartoon on the top, you can see that a heavy object can bend the space and time around it. And this curvature, this bending of space-time is what produces gravity. Very interesting theory. If you want to know more about this, you can check the LIGO India YouTube channel. So there were also some video exhibits on space-time curvature that were presented there. So now the interesting part is that the general theory of relativity, the theory of gravity, also predicts the existence of gravitational waves. So what are these gravitational waves? When we have these kind of compact stars that I just talked about, so like neutron stars or pulsars or black holes. So what happens is that these objects bend the space-time around them, and when there are any disturbances, then these disturb the space-time around them and generate gravitational waves. So now you can see in this in these animations that you can see in these animations that there are these compact stars which are going around each other. They could be black holes, that could be neutron stars, and these now emit gravitational waves. They lose energy, they come closer and closer and merge together. So these kind of interactions can produce gravitational waves. There are also other possibilities. So if there are isolated objects, so just single black hole or neutron stars, they can also have disturbances inside them. Something like we have earthquakes on Earth, so something like that. So these disturbances can also produce gravitational waves. Now, why are gravitational waves so interesting? Because like I told you, that even with our best technologies that with which we can scan the entire sky, these kind of objects which do not emit visible light cannot be seen, although they are the most massive and the most dense in the universe, but still we cannot see them. So how can we look inside them? How can we probe them? Because we want to probe them because we want to find out about the extreme nature of physics, what goes on inside these systems. These are like astrophysical laboratories which tell us about extreme properties of matter. So I told you about pulsars, right? So in pulsars or neutron stars, there can be also these disturbances. Like if they have very strong magnetic fields, they are also called magnetars. So these magnetic fields can distort them from spherical shape to a bent shape, kind of an elongated object. So that can also produce gravitational waves. There can also be kind of flares and outbursts and a lot of dynamic features which also produce some disturbances in this space-time around them and therefore generate gravitational waves. Now, the question is, can we detect these gravitational waves? And how can we extract this information about their interior from gravitational waves? So the other very interesting property is that these black holes or neutron stars, they could have different oscillation modes. Just like the earthquakes are also produced by these kind of oscillations. And stars also oscillate in the same way. And these oscillations also tell us a lot about the interior properties of these stars. So on Earth, the study of earthquakes is called seismology, you know, right? So these are called astroseismology. So this is an entirely new field in itself. Now, the question comes, how can we detect gravitational waves? So the first indirect detection of gravitational waves happened back in 1974 when Joseph Taylor and Russell Hulse, they first started monitoring a couple of neutron stars that were rotating around each other. So this binary of neutron stars, they were coming closer and closer together. Why? Because they were emitting gravitational waves. They were losing energy and falling towards each other. So now what Taylor and Hulse did was that they measured exactly this slowing down, not slowing down, but this coming closer of these stars, of the neutron stars towards each other into a merger. And what they found is what you can see in this figure on top. They found that the data falls exactly on the general relativity prediction that was given by Einstein in his general theory of relativity back in 1950. So this was the first indirect evidence of the existence of gravitational waves. So they were awarded the Nobel Prize in 1991 for this discovery. And not only that, it encouraged an entire community of astrophysicists who now wanted to observe these waves. So now efforts started all over the world in building big detectors to catch these gravitational waves and to analyze them. But this is a great technological feat, okay? It's a great technological challenge. Why? Because gravitational waves are extremely minute. So I will come to that soon. So here on top, the picture that you can see are the detectors, the LIGO detectors in Hanford and Livingston in the US. And on the right, you can see the Virgo detector in Italy. So before these, there were also many other efforts. Like Weber was the first one who built a bar detector, which tried to detect gravitational waves, but it was not successful. There were also detectors like Tama in Japan and GEO in Germany, which tried to build detectors to catch gravitational waves as well. But the problem is that you can see that in the bottom figure, here you see that these gravitational waves are actually extremely minute. They are very, very faint. And this is what is predicted by general relativity. So how faint are they? So you can see this clearly in something called a sensitivity curve, which is given at in the bottom figures. And these sensitivity curves, so the sensitivity, which means the change in say you have a ring of particles, and how much will this ring of particle moves when gravitational waves pass through them. So this sensitivity you can see on the left, this relative change in the length is 10 to the power minus 22, which means 1 divided by 10 with 22 zeros. So you can understand that how minute this is, right? It's like a thousandth part of a proton. So how can we catch such fine disturbances, such very weak disturbances so efficiently with ground-based detectors? That's a massive technological challenge, okay? So there are these interferometers which try to do exactly this. So interferometer means that there are these long arms of the detector. So these are like kilometers long, about 4 kilometers in the case of LIGO and Virgo. And there is a laser source which emits laser beams along one direction, which is reflected in another direction through a beam splitter and then caught with a photodetector. And any slight change in these arm lengths of 4 kilometers will be measured very, very precisely. And this gives us data about the frequency and the time scales of these gravitational waves. So now LIGO detectors that you see here in the pictures, so these had sensitivities very close. So this is already a very significant technological advance which was obtained in the past decade. And but however, unfortunately, you can see that we required even more sensitive detectors in order to actually catch these gravitational waves from compact stars. Now, efforts started to upgrade these systems. So from 2015 onwards, there were from 2010 onwards, there were efforts to upgrade these systems more and more. And why are they so technologically challenging? Because as you can see that they have to be very, very sensitive, you have to isolate these systems completely from the surroundings. So there cannot be any thermal noise, there cannot be any seismic noise. You have to completely isolate the system. So this requires very high level technology in lasers, in optics, in vacuum technologies, and so on. So now, um, this after this upgradation, this advanced LIGO detector was now ready to detect gravitational waves. So it was very close to the expected sensitivity that can catch these gravitational waves. So the first surprise came, sorry, I'll have to, right. So the first discovery came in on 15th of September 2014, and it was it was for GW150914, right? So we just celebrated the 5th anniversary of this first direct detection. And how did this happen? So there were a couple of black holes in a distant galaxy which were merging, and now this gives a characteristic feature called a chirp signal. So the signal is like when they come closer and closer together, it's if you hear a sound, it becomes like a shrill sound. And this is what exactly was detected by the LIGO Hanford and LIGO Livingston detectors. So this was the first direct detection of gravitational waves. This was an amazing feat, which was like opening up an entirely new window to the invisible universe, because of which the three pioneering scientists who proposed this project were awarded the Nobel Prize. Screen share stopped, right? So I will try again. Okay, can you see my screen? I think you can, right? Okay, thank you. So, because of this amazing discovery, the three pioneering scientists were awarded the Nobel Prize in Physics in 2017. And this started a global effort in detecting gravitational waves all over the world. There came many other discoveries after this. So, all these were black holes, but then there came even one fantastic new discovery, which was an exceptional one. So I will briefly mention what this is. So there was an event called 170817 because this was observed on the 17th of August 2017. And what happened here was two neutron stars were found for the first time. Two neutron stars were observed to merge together. And not only that, you can see in this animation that when they merged, they gave out electromagnetic signals as well, which were observed with all our existing telescopes, like in gamma rays, X-rays, and so on. And this confirmed many of the different existing theories. So you can see that the Fermi and integral telescopes, they were able to see the same gravitational wave source in gamma rays. The Chandra telescope observed it in X-rays. The radio VLA observed the same thing in radio, and so on. And so this confirmed the theories which said that neutron stars merging were able to produce these different kind of observations like kilonova and so on. And even it confirmed the existence of some elements which are produced in neutron stars. So earlier we did not know where heavy elements are produced in the universe. So now from the observation of spectral lines coming from these sources, it was now found that neutron stars so these merging of neutron stars are from where we are able to, so the universe produces elements like gold, silver, and platinum. So all these that we see around us, these precious heavy metals, so these are produced inside merging neutron stars. So this was an amazing discovery. So now you can understand that how much we are able to explore these events in the universe only through gravitation, not only through gravitational waves, but also something which is called multi-messenger astronomy, which means that not only gravitational waves, but we can now see the same objects in gravitational waves and with different telescopes, and it opens up an entirely new window to the universe. And not only that, now these merging objects also tidally deform each other, something like this, the sun, moon tides that we have on Earth. And these tidal deformations also tell us about properties of dense matter inside neutron stars. So this is really an amazing discovery. It has opened up an entirely new universe for physicists. So, one last slide about the LIGO discovery. So now more and more objects are being discovered like this. So black holes and neutron stars, and not only that, we are finding out more and more objects which are even intermediate between these two. And these are opening up new questions and trying to answer these with the help of gravitational waves. So looking towards the future, so now, as I mentioned, that now there is this entire global effort being, advanced LIGO was called the second generation, and now we will have even better technology. So it will be called the third generation gravitational wave detectors with better sensitivity. And not only that, it will also help in localization of these sources because it is at a different geographical location than the other detectors. So the LIGO India project is really going to be a very exciting project, which is the next generation in gravitational wave detector, the LIGO India scientific collaboration. And so let's now look at the women who are contributing to the LIGO India project. So there are faculty members, research and development scientists, project engineers. There are a large number of postdoctoral researchers and PhD students. And of course, there are also interns and other administrative officers. So if we look at institute distribution, so roughly, so this is for this year, you can see the present scenario. So IUCAA has a lead contribution in this regard. and there are also women scientists participating from several other institutions. And you can also see in this chart that there are different categories in which these women are contributing. So there are quite a large number of PhD students and scientific officers. There are also faculty members. And of course, as I mentioned, there are technical, scientific and technical officers who are contributing to this project as well. However, as you probably have already heard, that women scientists are still lagging behind. We need to improve the gender ratio, and there are different efforts being made all over the world and also in India for this. I want to mention the Working Group for Gender Equity in the Astronomical Society of India, of which I am also a member. So we are trying now to close this disparity between male and female participation in astronomy in India. So let's look at what are the future opportunities with LIGO India. So in LIGO India, as I already told you, it is the next generation of gravitational wave detector technologies, which means that it needs to meet very high challenges in many different areas of specialization. You can see that not only gravitational wave science, which is already a multidisciplinary field where you have gravitation, you have electromagnetic counterparts, you have nuclear physics, particle physics, and so on. There are also many other challenges. There are fields to contribute, like in mathematics, for modeling, for parameter estimations, for modeling these objects, for data analysis, for extraction of these data, for computation, data science, and of course, engineering challenges like optics, electronics, and mechanics. So LIGO India has many long-term training programs starting from undergrads and postgraduate students. And there are also many training and development modules which are developed in association with the different participating LIGO India institutions, as well as international collaborations, which finally produce the skilled workforce that we require for LIGO India. So if you're looking for opportunities with LIGO India, you should definitely check the website and also the gw.iuca.in research opportunities, where there are a lot of different upcoming opportunities that are listed. There are internship opportunities for undergraduate and postgraduate students, not only at IUCAA, but also at these other LIGO India laboratories all over the country. In IUCAA, we have different master's, BTech thesis research projects, and these span over fall semester, spring semester. There are also summer projects which give the interns and students hands-on experience to work on these different technologies that we require for LIGO India. There are also many different international opportunities with LIGO India. There is the International LIGO SURF program, which is the LIGO India Caltech Summer Undergraduate Research Fellowship. There are Future Research Talent Travel Awards of Australian National University. There are also summer projects at the Institute for Gravitational Wave Research with the University of Glasgow. And there are also many other interesting workshops and training programs, like we have the Finesse Workshop and Hackathon, where there is a hands-on interferometer modeling scope with mentored training program. So if you want to know more about this, definitely check the LIGO India website. And also you can fill out the application form that has been meant for undergraduate research opportunities in gravitational wave physics. So not only, and Manasa has talked about the detector technologies and so on. So you should definitely go through these lecture series if you want to know about where exactly the technology needs to be developed for LIGO India. Finally, you can also get a lot of information about gravitational wave science and participation of women in such projects from the LIGO India blog called Gravity Matters on the website. We also have a section called Glorious Women in Astronomy, which features the participation of women in the LIGO Scientific Collaboration and LIGO India project, and also very interesting features about the challenges that they face in everyday life, and their achievements, their awards and books and they have written, and so on. So please look into the resources that are there in the websites associated with LIGO India, the social media channels, Facebook, Instagram, Twitter, the YouTube channel. Look into our blog, and we also have a podcast called Listening to the Cosmos, which will give you a lot of information about this very exciting mega science project, which gives a lot of opportunities for Indian girls to participate in the future. So thank you very much, and also feel free to contact me if you have questions. Thank you.
Hello, madam. Hello.
Yes.
Hello. Madam, myself Ashna Batra. Madam, I just read that there is one education competition regarding the women in science. I just wanted to know when is the due date for that submission. I would like to participate. Yes.
I'm sorry, due date for?
Due date for the education competition. There was one link which was posted last week. The
Oh,
same
that
where they
was.
had posted.
I have to check that, but I think probably that was for National Science Day if it is last week.
Yeah. So the due date is over.
Probably, but you can write to the LIGO India, the outreach team.
Okay.
Okay, so you can send us the question, and yeah, we will get back to you.
Okay. Thank you so much, madam. Thank you.
Yeah, no problem. So if there are questions on Zoom,
Yeah.
I can let me see if there are any questions on chat.
If the participants have any question, they can post it in the chat box. It's a very nice presentation, and I have one question. I
Yes.
didn't understand how do you extract the details about the source of the gravitational wave? I mean, how do you know that it's coming from the neutron star or the black hole?
So there is a lot of modeling involved in this. So there are many scientists who are working on this. So first of all, there are development of models. So you theoretically try to model this, and then you compare it with the observation. So usually this is done through a technique called template building. So you make a template, you try to match it with the observations, and then you try to see whether it matches exactly or not. And then once you have the data, then there is something called extraction of physics, right? So this also needs a lot of effort from simulations and theoretical modeling in order to understand what's going on and which kind of source it's coming from.
Okay. One of our visitors has a question that about the difference in the type of sources. I mean, why the gravitational waves from the black holes are more in number than the neutron stars? I mean, why the gravitational waves coming from the neutron star are only a few, whereas for the black holes there are more?
This is an interesting question. Yeah, actually, so this gravitational wave detections have actually now they are producing more surprises than we have expected. So when the first detection was made, we were not even sure what would be the number of sources and that will be detected, right? So now we can see that there are all these black holes which are of different types of origin. There are the supermassive black holes, there are the black holes which are found at the endpoint of the lives of stars and so on. And these are we are actually first for the first time as well, we are finding out how massive these stars are and what is the spectrum. So there are actually many interactions, right? So we are not even sure what are for some objects like you saw in the picture. Maybe I will share that slide again. Um, so in this picture, you can see that these electromagnetic black holes in purple, these were the ones which were actually seen with telescopes. I mean, not directly with telescopes, but with the interactions black holes have with the surroundings. So you see that they were only like 5 to 10 times that, as heavy as the sun. And for electromagnetic neutron stars, we thought these are more 1 to 2 times that of the sun. But now with gravitational wave detectors, we have more surprises. We actually see way more massive black holes than we had earlier known about, right? And also the same, that we are now finding objects which are somewhere in this mass gap, which we thought existed earlier. We thought that black holes and neutron stars were actually having different masses. So now we see objects populating also this mass gap between them. So I would say that this is a surprise for us as well. And with gravitational waves, we are finding out more and more about these features of black holes. It's opening up new questions as to why there are so many black holes, and why and what kind of masses they can have and what are their origins. So this is research in progress. I hope that answered your question. Also, Radha mentions that she was part of the LIGO India outreach program. Okay.
Okay, one of our visitors is asking that where in India LIGO is setting up this lab.
So the LIGO India project, like I mentioned, it is coming up in Hingoli in Maharashtra. I think I showed this in a slide. Let me go back there. So yeah, you can see here in the inset. So it's coming up near the Hingoli district in Maharashtra. So this is like the schematic picture of this site. But like I also mentioned that although the site will be located here, but there is a national effort in in this entire project. So there are some key institutions which are handling the technological needs, but there are also a bigger LIGO India scientific collaborations with many more institutes from all over India. Any other questions?
Yeah. Okay, you showed many institutions are taking part in LIGO India, but what are the responsibilities? I mean, the distribution of work, whether instrumentation or software, some responsibilities. Is there any distribution throughout the institutes?
Yes. So actually, if you probably yeah, maybe I can share this. So if you can you see my screen, right? So I'm sharing the LIGO India website. So if you go to the LIGO India website, you will also find a lot of information about these institutions and what have been their contributions. So for example, GCSEM is working on the basic infrastructure design. IPR has conceptualized the basic infrastructure design. They are also working on vacuum systems, implementation of the CDS system. IUCAA mostly looks at computation, data analysis, and also the science, gravitational wave science part. The RRCAT Institutes handles the optics, the third generation R&D, hardware, detector integration, integration and so on. So you will find a lot of information about these participating institutes if you look into the LIGO India .in institutions.
Okay, I see there are no more questions from the audience. Okay, I'd like to thank once again Professor Debarati Chatterjee for this very nice and informative talk. I hope many people have been helpful because of this lecture. I hope there will be many more questions coming in future as well. I'll request all the audience also to attend all the lectures of our lecture series. I would like to thank Professor Chatterjee. Thank you very much.
Thank you very much to all of you. And please, like she mentioned, do attend the entire lecture series because it mentions participation of Indian women in all these mega science projects. So thank you very much.